This is a structural equation model. Notice that it covers all of the elements that I just listed. It has latent and observed variables. Some of the variables, whether they're latent or observed, are linked together by paths. That's the structural part. And now we can see how the literal notation can be mapped on. And I'm going to reiterate this mapping on the next slide. However, the point here is to visually see that there are 3 measurement models, and they're linked together through the structural part of the model in the middle. These 2 main parts, the measurement parts and the structural parts, are what make this technically a structural equation model. So here are the elements to the model, and specifically the free parameters that we're going to estimate. This slide and the next slide are by far the most notation for the entire course, because they both include essentially all of the notation wrapped up into a single model. So if you get lost in Greek, don't worry. I will walk you through the elements of the input that are linked to all of this notation, and that will help you to understand the important parts and also how to implement it in Mplus. So we have observed items that are linked to the latent factors through loadings that we call lambda, and we can see them up here. They're linking observed items to loadings. We also have error variances that are associated with these observed items. We have some down here and some up here. And these I'm going to call a couple of different types of notation. So it's very easy to think of them as sigma squared because they are variances, and that's easy notation to remember for a variance. But they're actually also elements in the big upper boldcase theta matrix. So we can denote these individual elements as little thetas, and that will show that they are single elements within the large covariance matrix. Specifically, if we are talking about variances, these would be the diagonal elements of theta. And so we can have 2 different types of notation here. They mean the same thing. They're talking about these elements, these circles. You have variances for each of those listed up here and then also down here. 2 pieces of notation. Next, we have the latent factor covariances called psi, and that is in a covariance matrix. We don't have these covariances in our model, but they still can exist, and we actually saw them in the CFA lesson. Then we have disturbances called zeta, which can be linked through a covariance matrix, which we call omega, if we had such a thing. Then we have regression paths here in the center. So we have gammas and betas, and this depends on whether they're linking together exogenous or endogenous variables. And then finally, we have big phi, which is a covariance matrix for the exogenous variables, if you had such a thing. So here are the priors next that we can map onto all of these model parameters. We're going to use 3 different prior distributions. We will use a normal, an inverse gamma, and an inverse Wishart. So although this slide is very messy, it really only has 3 pieces of prior information on it. Which parameters are normally distributed, which ones are distributed inverse gamma, and then finally, when do we use an inverse Wishart prior? So loadings and regression paths are distributed normally. We have normal distributions on them, and those normal distributions are governed by a mean and a variance hyperparameter. Anytime we have a variance, like we see here, we can use an inverse gamma distribution. That's governed by a shape and a scale hyperparameter. And then if we were to have an entire covariance, which we see potentially one here, here, and here, we can use a multivariate prior called an inverse Wishart prior. And that prior has hyperparameters. The first one is a positive definite matrix. The second one is a degrees of freedom hyperparameter. So I'll say There's a lot of notation here, but just to try to keep it straight, we have loadings and regression paths. Those are normal. Any variances are inverse gamma, and then covariances are always inverse with sharp. All right, so here's the code. I'm using data from Ken Bullen's classic book on SEM from 1989. This is political democracy data, and I reran his model and data in the Bayesian framework, and I'll show you the results and how to play with prior settings later. This model maps onto the diagram that we saw just a moment ago, where we have 8 y variables and then 3 x's. We're going to form 3 different latent factors and then connect them through a structural model. So I can change the sampling algorithm if I wish, and you would do that with this line of code. And then down here, we can change the minimum and maximum number of iterations we request in the chain. I'm using the default setting of 2 chains here and using default priors here, but we'll modify that to look at subjective priors in a bit. So here's the model setup. Notice that I can label a lot of it. So this first part of the model, these are the loadings that create the 3 measurement models that we saw before. So we have our observed items that are loading onto a latent factor that we name. And we know that they're loadings because we're using this by notation. And we can give a label to each of them, which we will use later if we want to override the default prior settings. This is the measurement part of the model. Next, we have the structural part of the model here. These are the 3 paths in the center of the model that linked the latent variables together. I can also give those labels and potentially change the priors on those using these labels. Next, we have some correlated error variance terms in the model. If we go back up to slide 4, we can see them here. Not all of them are allowed to correlate, but some are. And this is the original mapping of what Ken Bullen did in his book. So I just mimicked that here as well. And we can add those into the code with the with statements to denote that they're allowed to covary. So the next part of the output or the input will ask for output. So specifically, we can ask for Tech 1 if we want any type of standardization to be spit out. We can ask for our MCMC information to be saved out in a file that we can read into R later. And we can ask for plots if we're interested in those. So now we can take a look at the output. We can see an initial summary of the results in the output. And this part is simply just restating what our variables are called and what role they are playing in the model. Next, we can see information about the estimation algorithm that's being implemented. Most of this was default settings with a couple of exceptions that we went through and modified. Then we have results. So these results can be mapped directly onto the model diagram if you want. First, we see the measurement model results. These are the by statements. These are for the 3 CFAs that we embedded within the model, where we created 3 different latent factors and had specific items load onto them. The first loading for each factor is set to 1.0 to give that factor scaling. And then we get loadings below for the rest of the items, and these are in an unstandardized metric. So this is the measurement part of the model. Next, we have the structural part of the model. And these are the 3 regression coefficients that we wanted to have estimated, the gammas and betas, in the center of the model. This is where we have our on statements that can link those measurement models together through the structural part. So next we see the with statements that linked some of those variances at the top of the diagram together. And these are estimates for those parts of the measurement model. Next in the output, we would get intercepts and variance that's tied to the exogenous latent factor. And then we have those error variances, and then we have variances that are tied to the endogenous latent factors that we included in the model. After that, the output will produce standardized results, and it may be that those would be more informative to us. It depends on our scaling and our understanding of the variables, but Mplus will give us a variety of different standardizations. And if you request these, they would appear next in the output. And it would really depend on your decision on which type of output you want to be describing in your paper, whether it be unstandardized or one of the standardized solutions that Mplus can give you. Next, we see Tech 1, and this is where we haveMplus's internal numbering system, where we see the number that it gives to every parameter that's estimated. Then we have starting values and our priors. So I'm not going to show you all of them because there are a lot, but we can see the loadings and intercepts and paths that are normally distributed. And then we see variances that are distributed inverse gamma. These three right here are the factor means, I think. And so all of the different priors that we would use would be listed here. If we had included a full covariance matrix, then we would also see an inverse Wishart prior listed here. But our model did not have such a matrix, so we have a bunch of inverse gammas that were included. But all of the priors would be listed, and it's always a good idea just to check them, even if you use default settings, to make sure that what you intended to be estimated is actually what happened. Then Mplus will tell you what plots are available, and that the MCMC information was saved in an extra file if you wanted to read into R. So these sections of output are all the same across the different model types that we've covered up until this point and will continue to cover. But I think it's helpful to see how Mplus displays the results in a really comparable manner, even when we're dealing with different types of models. Next, we can look at how we would specify informative priors. So here we have the model code with the by statements. These are the measurement models. And we have labels or coding next to each of those loadings. And then we have those regression coefficients as well. Each element here also has its own label. These labels are what allow us to use user-specified priors for. Next, we have our with statements, and if we wanted to specify our own priors for them, we could give them loadings as well. But this slide shows you exactly how you would do this. So I pulled out just a few of them, and we can replace the default diffuse priors with user-specified priors. So let's say we were interested mostly in having user-specified priors on the factor loadings. We can name them X1 to X3 and then Y1 to Y8. And then we would take the free loadings, so not the ones that are fixed to 1.0. We could take those free loadings and then place our own priors on them. We can use the model priors code command and then say each one is distributed normally because it is a factor loading. It has a mean and it has a variance hyperparameter. You could give these priors any setting that you want. I just show you how to do it here, but these numbers don't mean anything substantively. So N is used for the shorthand for a normal prior. If you wanted to have an inverse gamma prior that you're overriding, you would use IG. Inverse Wishart would be IW.